What's up everyone, this is Dariusz Kalbarczyk, co-founder of AIMP Poland, JS Poland and AI Poland. Welcome back to the AI Master Podcast. Today's guest, joining us from Germany, Director of Sales EMEA at Tenstorrent. Ladies and gentlemen, Christian Stenzel. Christian, how are you?
Thank you, Darius. I'm really good and so excited to be here.
For those who don't know you yet, please tell us about yourself and what you do.
Yeah, as I said, so I'm actually Christian. I'm based in Germany, close to Munich, and I'm the director of sales at Tenstorrent.
How would you describe what Tenstorrent does and what makes it unique in the AI hardware space?
Okay, so Tenstorrent was founded back in March 2016, and I think we already have more than 1,000 employees. I'm not actually keeping track of the numbers, but we are really growing fast. What we build is AI processors, which we call Tensix AI cores, and RISC-V based CPUs. And those are really designed to scale from edge devices to data centers. So those RISC-V and Tensix AI cores, they are our fundamental IPs or building blocks in our ASIC chips. And with those ASIC chips, we build PCI Express cards, servers, desktop boxes for AI workloads. So in my opinion, what the company really makes it stand out is our modular chiplet architecture, our open source philosophy, and our full stack approach that combines hardware, software, and systems. So what that really means is that instead of just making accelerators, we aim to deliver flexible, customizable AI compute platforms, giving customers more control, efficiency, and scalability across different AI workloads. And you probably know Jim Keller, that's our CEO, which is really an industry legend, and Jim has been very instrumental to the success of Apple, AMD, and Tesla, and he's now driving our open future. And I guess we will touch base on this a little bit later.
Own your silicon is such an intriguing idea. What does it mean in practice for AI developers and the wider tech community?
Yeah, absolutely. Good question. So own your silicon means that giving AI developers and companies really control over the chips they run on. So rather than relying on closed proprietary hardware from big vendors. So what that means in practice is that we, with our RISC-V architecture and Tensix AI processors and our modular chiplet design, we let developers customize or even license the technology itself. Tailoring performance, power, and features to their own AI workloads. For the, for the wider tech community, it really promotes hardware transparency, flexibility, and innovation, enabling startups, researchers, and enterprises to build differentiated AI systems instead of, just being locked into someone else's ecosystem.
Tenstorrent has grown rapidly, expanding across the world and raising over $1 billion. How has that growth shaped your mission and strategy?
That's really a lot of money, right? So I'd say, in my opinion, first of all, it's really a testimonial that our investors are really buying into our strategy and vision. Our rapid growth and our global expansion have really reinforced our mission to democratize high-performance computing by making AI hardware more open, scalable, and accessible. And, with over $1 million raised, we were able to accelerate our R&D, expand partnerships, and build a worldwide team that combines silicon, software, and system expertise. This scale allows us to move faster towards our vision of modular RISC-V based platforms that serve everything from edge devices to massive data centers, and staying true to our goal of enabling developers and enterprises to own and shape their own compute future.
You often talk about open hardware and open software. Why is openness such a key part of Tenstorrent's philosophy?
Yeah, this is really critical because, openness we think is really central because it empowers innovation and collaboration across the AI ecosystem. By building an open standard, like RISC-V, the Tensix AI course and the end-to-end software stack, Tenstorrent allows developers, researchers, and companies to inspect, customize, and improve their hardware and software stacks instead of being locked again into proprietary systems. And we think the openness drives transparency, and we see that, and flexibility and long-term sustainability, enabling a wide range of community to co-evolve AI infrastructure together. It's really about creating a world where anyone and everyone can build, optimize, and truly own the computing technology that powers their new ideas.
Let's dive into the core of your technology, the Tensix AI processor. What makes its architecture different from other AI chips out there?
Yeah, so the Tensix AI processor stands out because it is scalable, modular, and is really designed to efficiently handle a wide range of AI workloads. Unlike fixed function accelerators, Tensix uses a data flow architecture that dynamically routes computations and making it highly efficient to both training and inference. It also features many lightweight compute cores working in parallel, delivering high throughput without the heavy power of the heavy draw of traditional GPUs. It's like a 2D torus. That means every Tensix has a connection to its neighbors, north, south, east, and west. Tensix is also very fully programmable, giving developers more control to optimize for specific models or frameworks instead of being locked into a rigid hardware behavior. And there is also scalability through chiplets. That really, the design allows multiple Tensix processors to be combined into a larger system, offering performance that scales up or down depending on the application. And last but not least, our software stack, right? It's supported by the software stack, making it really easy to map complex neural networks efficiently onto the hardware. So I'd say in short, Tensix is really built for flexibility, efficiency, and scalability rather than one-size-fits-all approach which is common in many AI accelerators.
You're combining RISC-V CPUs cores with Tensix AI cores on the same die. Why is that integration so important for modern AI workloads?
Yeah, that's like the question. So that's really an important question. So integrating RISC-V CPU cores with Tensix AI cores on the same die is critical because modern AI workloads aren't just about the raw matrix math. They really require tight coordination between general purpose or specialized processing. So whilst Tensix cores are ideal for big math operations like vector calculations, matrix arithmetic, or large data sets, the RISC-V CPU cores are ideal for traditional math, conditionality, along with high performance and robust programmability. So in a nutshell, so merging Tensix cores and CPU cores on the same die lowers latency, boosts utilization, and increases machine learning performance. And machine learning developers need both, really, CPUs and AI cores to build dynamic models of the future that are not possible today due to latency and utilization problems of using the host CPU.
You've mentioned that current systems face latency and utilization challenges when relying on host CPUs. How does your approach overcome those limits?
Yeah, so current AI systems often rely on external host CPUs to manage data movement or task scheduling or coordination. And this is really the problem. So this leads to latency bottlenecks and underutilized accelerators. Our approach really overcomes those limits by, as I said, embedding RISC-V CPUs directly alongside with Tensix AI cores on the same die. So this tight integration enables, for example, on-chip orchestration. So the RISC-V cores can directly manage workloads, memory, and task scheduling without constantly communicating back and forth to an external host. It lowers the latency because data really stays on the chip, reducing the round-trip time between CPU and accelerators. The AI cores also have high utilization because they spend more time computing and less time waiting for instructions or data transfers. And the performance is really scalable. So multiple integrated units can be linked together efficiently, maintaining high throughput as systems grow. So in an essence, by merging control and compute in one cohesive architecture, we really eliminate the traditional CPU accelerator bottleneck, delivering faster, more efficient, and better utilized AI performance.
Could you walk us through how the TT-Forge compiler and the TT-AI software stack helps developer get the best performance from your hardware?
Let me try to illustrate that a little bit. So just think about the picture. I'm going now top bottom in terms of the stack here. So TT-Forge, that's our kind of MLIR based compiler, is accepting common frameworks like PyTorch, TensorFlow, or accept formats like ONNX and JAX. And there are already more than 100 models running without any issue. And they're basically also open source on GitHub. Walking down the stack, there is TTNN, which is a Python and C++ neural network operators library, which is used to build models. One step down, there's TT-Metal or TT-Metallium. This is really a low-level programming model, so to say, a framework that enables kernel development. And at the bottom, there is TT-LLK. That is a low-level Tensix kernel, like primitives, which implement foundational compute like matmul, GLU, ReLU, etc. So the TT-Forge compiler and the TT AI software stack are really central to how developers unlock the full potential of Tenstorrent's hardware. They bridge the gap between high-level AI models and the underlying Tensix architecture. So to explain this a little bit in more detail, so TT-Forge takes models from common frameworks, as I said, PyTorch, TensorFlow, for example, and automatically maps them onto Tensix cores, optimizing memory use, data flow, and parallelism for peak performance. There is also hardware-aware scheduling, so it understands the chip's topology and distributes workloads in an intelligent way, ensuring every core and memory block is fully utilized. The software stack provides a consistent environment from model import to runtime, so developers don't need to rewrite code for different systems or chip configuration. And because it's built on open standards, developers can fine-tune or extend the stack for custom workloads or new AI architecture. So it's really scalable. So the same software tools work seamlessly across single chips, multi-chip systems, and data center deployments. So all that means is really that TT-Forge and the stack make Tenstorrent's hardware as easy to program while still delivering the performance and efficiency and flexibility that come from its unique AI architecture.
Many of your tools like TTNN and TT-Metallium are open source on GitHub. How does open source community contribute to Tenstorrent's progress?
Yeah, it's really important because that's our philosophy, right? Open sourcing everything. So TT-Forge, TTNN, TT-Metallium, TT-LLK. That's really a key part of our strategy, as I said, to build on open, collaborative AI ecosystem. And the open source community is contributing in several important ways here. Developers around the world can experiment with Tenstorrent software, suggest improvements, and help optimize performance for new AI models. This really accelerates progress far beyond what an internal team alone could really achieve. In that way, the ecosystem is also growing. So open tools attract researchers, startups, and enterprises to build on top of Tenstorrent's platform, expanding the ecosystem of supported frameworks, models, and use cases. Open source also comes with trust. So sharing the software stack openly allows users to understand how workloads are executed and optimized. And it's a cross-pollination of ideas. So collaboration with RISC-V and AI open source communities brings fresh perspectives and helps align Tenstorrent's technology with emerging standards. It also attracts talent. So open source projects naturally draw skilled contributors and future customers who are already familiar with the tools and hardware. So what naturally happens by making open is that we turn our developer community into co-innovators, striving for faster, broader, and more sustainable progress in AI computing.
Tenstorrent is also a strong advocate for RISC-V. Why do you believe RISC-V has the potential to become the CPU for everyone?
That's very important. It's, as you know, RISC-V is an open source CPU architecture and is really, really getting bigger every year. There is existing full support in software, OS toolchains, and debug, and the rapidly growing community is contributing to it accelerating maturity and adoption. The instruction set is modular, so it allows for customization, letting designers and adding their own extensions, enabling CPUs tailored for AI, automotive, edge, or data center applications. Everyone and anyone can build on RISC-V, from startups to global enterprises, lowering the barriers to innovation in hardware design. And furthermore, this has become even more important, unfortunately, with the global situation, RISC-V becomes with strategic independence. So companies and nations can design their own chips without relying on proprietary architectures like x86 or ARM. It is really a processor for everyone, promoting tech sovereignty.
Your Ascalon CPU project looks impressive. How does it fit into your broader AI strategy?
Today we compete in the AI accelerate and GPU market with our wormhole and black hole technologies. So black hole is our latest technology, but we think the workload of the future will require high performance vector, matrix, and scalar arithmetic. So the computer of the future will have a tighter integration between traditional workloads and the deep learning workloads we have seen become so popular.
You've described chiplets as the next frontier. How do they change the way we think about scalability and efficiency in AI hardware?
Yeah, that's a very good question. Thanks for the question. So chiplets are indeed the next frontier because we think and believe they will completely change how scalability and efficiency are achieved in AI hardware. So instead of building one massive monolithic chip, chiplets allow designers to combine multiple smaller specialized dies into a single system. This is just like building blocks for compute. We think it will really transform the landscape because it's a modular scalability. So chiplets make it easy to scale performance. You can add more compute or memory or I/O chiplets as needed without redesigning the entire chip. The yields are higher because smaller chiplets are easier and cheaper to manufacture with higher yields, reducing waste and improving cost efficiency. You can mix and match different types of chiplets like we do with RISC-V CPUs and Tensix AI cores and memory to really create customized solutions for specific workloads. It's also easier to upgrade systems, right? New chiplets can be swapped in without changing the full system, accelerating product development. So you have faster innovation cycles. And so the short on-package interconnects between chiplets reduce latency and power consumption compared to external communication between separate chips. I'd say, chiplets are like Lego-like scalable, allow scalability for AI compute, letting us and our partners build tailored, efficient systems, all from a modular and reusable foundation.
You've talked about creating an open chiplet ecosystem. What kind of collaboration do you imagine there, and how can others be part of it?
Yeah, the OCA Open Chiplet architecture, I think it has been renamed now to Open Chiplet Atlas, and the ecosystem will democratize chip design, lower development costs, and accelerate innovation, enabling heterogeneous chiplets for plug-and-play interoperability. There are now, I think, more than 50 partners involved in the ecosystem, from leading semiconductor companies and global conglomerates to academic institutions. So, as we discussed earlier, monolithic system-on-chip designs have become increasingly complex, expensive, and time-consuming. This doesn't really make a lot of sense, right? So the Open Chiplet Atlas ecosystem directly addresses this challenge by defining a complete modular open source approach to chiplet interoperability in physical, transport, protocol, as well as system and software layers. The OCA ecosystem is fundamentally a collaboration endeavor. So all specifications, frameworks are being developed with transparency and are available on a royalty-free basis. So in that way, we are ensuring a level playing field for the entire industry. We and our partners believe that the most robust and innovative solutions emerge from a diverse community of contributors. And we strongly encourage companies, academic institutions, and individuals to join this effort by contributing their expertise and help to shape the future of composable silicon. So please check out www.openchipletatlas.org.
The black hole system includes 140 Tensix processors and 16 RISC-V CPUs. What types of workloads is it designed to handle best?
Yes, indeed. So for example, the P150 cards, they have, that's a black hole card, has 140 Tensix cores and 16 RISC-V cores. By the way, we are currently in bring up, so that means testing and verification of our P300 card, which is hosting 2 of those ASICs, doubling the amount of Tensix and RISC-V cores. This will probably take a few more quarters or some more time until we really can release the P300 card to customers as production versions. But stay tuned. But back to your question, I'd say there isn't really much of a limitation here. But let me try to double click down on that a little bit. So with the 140 Tensix processors, Blackhole delivers exceptional throughput for deep neural networks, including transformers and generative models used in NLP vision and multimodal AI. 16 integrated RISC-V CPUs, they manage data flow, orchestration, post-processing, enabling full AI pipelines to run efficiently without heavy reliance on the external host, as we discussed earlier. Overall, I think its architecture scales up and out, making it ideal for server clusters performing distributed training or inference workloads. So the combination of high compute density and programmable cores also fit best for high performance computing HPC and simulation tasks that demand both precision and parallelism. And a very important point, by the way, we do not use expensive HBM. We just use GDDR6, which is a fraction of the cost. So I'd say in summary, Blackhole is optimized for AI at scale, from large language models to advanced computer vision, balancing raw compute power with flexible on-chip control through its RISC-V and Tensix integration.
The Tenstorrent Galaxy server scales things up even more. How do you manage such a massive throughput while keeping performance stable?
Yeah, that's a good question. That's a beast, right? The Galaxy server. So Galaxy is built from interconnected boards packed with Tensix and RISC-V processors. So each module is a self-contained compute unit. So scaling up simply means adding more modules. And performance grows linearly while remaining predictable. So by the way, we use Ethernet to connect those modules internally, but also for scale out because there's no such limitation like at competitors. So any topology is possible. We do have a distributed workload management, so embedded RISC-V CPUs handle orchestration locally, allowing each node to manage its own scheduling and data flow instead of relying on centralized hosts, keeping utilization high across the system. Our advanced cooling and power management features maintain consistent performance even under heavy sustained AI workloads. And last but not least, software. The TT software stack and the TT Forge compiler automatically balance computation, communication, and memory use across the cluster, ensuring stable throughput at scale.
You've mentioned TT train and redundancy for AI training. How do you ensure reliability when operating at that kind of scale?
Reliability at scale is critical for AI training, especially when systems are running thousands of parallel processes. This is really early days for Tenstorrent, but we have been running experiments to prove our scale-out capabilities even on our small and medium systems. So what we're having today is a closed set of Loudbox systems. They're all interconnected via our Ethernet fabric, which has been used to train multi-layered perceptrons and execute LoRa on other small language models. So what this proves is that we have the capabilities to drive not just high-performance inference, but tackle the bigger training workloads on exactly the same architecture. It also helps to prove our scale-out strategy is being efficient and delivers sufficient throughput.
Tenstorrent has teams spread across Austin, Warsaw, Seoul, and more. How do you keep those teams aligned when developing such a complex hardware and software together?
Yes, there's also a small office in Munich nowadays, and we keep growing worldwide, really. Yeah, we are sort of all over the place. We share the same vision of open, scalable compute. Tenstorrent employees really have a strong engineering culture. So that means the company prioritizes technical leadership, mentorship, and autonomy, empowering teams to move fast while staying aligned through shared goals rather than top-down control.
You've said your mission is to make AI and silicon cheaper, open, and fun. What does fun means to you in the world of chip design?
You know, the word fun speaks to creative freedom and engineering joy. That is, unfortunately something that is often missing in the traditional closed rigid world of chip design. So working in an open ecosystem where hardware and software co-evolve invites collaboration across disciplines and geos, turning engineering into a shared creative process. So the freedom to innovate while embracing openness, as we discussed earlier. Our engineers really enjoy pushing boundaries, rethinking how compute is structured, challenging the status quo of closed systems, and exploring bold architectural ideas. That's fun, right? Isn't it?
Exactly, it is. How do you see open silicon evolving in the coming years? Could it have the same impact as open source software did?
Oh, yes, absolutely. And thanks for that question. So open silicon has really the potential to be as transformative for hardware as open source software was for computing. It is, the same principles, accessibility, collaboration, transparency, and innovation are now being applied to chip design. Democratizing of hardware will lead to an explosion of innovation far beyond what any single company could achieve. And, as open silicon matures, we will see a growing ecosystem of reusable IP blocks, open verification tools, and shared design standards, just like what Linux and open software libraries created for developers. So sharing innovation reduces duplication of effort, cutting both time and costs to bring new silicon to market. And open hardware encourages tighter integration between hardware designers and software developers, enabling systems optimized for top to bottom. And it invites collaboration across academia, startups, and nations, fostering tech independence and shared progress.
Okay, and finally, what next for Tenstorrent? What are you most excited about as you look throughout 2026 and beyond?
Yeah. So looking ahead to 2026 and beyond, we're really focusing on scaling our open vision. So bringing together our RISC-V CPUs, Tensix AI cores, and chiplet-based designs into a unified ecosystem that can power everything from edge devices to massive AI data centers. And I'm part of this journey, and this is really what is exciting me most.
That was my last technical question. I still have a few non-technical ones, if I may.
Sure.
What music do you listen to while working, if any?
So interesting question. So I'm usually not listening to music whilst I'm working, but if I'm not working, I'm listening to mainly rock music, but also some sort of pop music, but more the old stuff, like for example, Green Day or Metallica.
Oh, Metallica, Green Day, I love it.
Okay.
If you weren't working in tech, what other profession would you like to try?
I have never thought about this, to be honest, because I really love to work in tech. So I do have a technical background. When I started my career, I was really hands-on writing code. And then I moved into sales because I really love to talk to people and be in meetings and also travel. So honestly, there isn't really any other choice, to be honest.
What's your favorite way to unwind after a busy day of working?
Well, this is really my children. So I have 3 children, and there are 9, and the twins are 6, and they're keeping me busy when I'm not working, and also grounding me somehow, because it really you immediately have to switch gears from tech world to business world to whatever your action items and deadlines to being a father and taking care of your family.
Exactly. And the last question, how do you stay motivated during challenging projects?
It is really the people I'm working with, but also the customers I'm working with, and how really the great future ahead of us, as we discussed in the podcast. So that really motivates me every day to get up and do my best to contribute to this journey and make things happen.
That's all for today's episode of AI Master Podcast. Christian, thank you so much for joining me and sharing your insights on the future of open AI hardware. It's been a fascinating conversation. If you enjoyed this episode, don't forget to subscribe on your favorite platform and share with your friends or team. You can also find more inspiring talks and interviews at kalbarczyk.tech.